As many can attest, when you join the Globebusters community, you are given a new set of eyes. Now, we've studied Earth science before, but now that we've been given a new set of eyes, it is time to go back and tell you what we see. This is Modern Earth Science Destroyed. Hello, welcome everyone to Globebusters. Way happy to be here with this new theme going on right now. There's been a lot going on. I'd love to let's jump right into it and introduce the panel. Karen, you've got a lot going on over there with you. How was Coffee Talk on Monday?
It was good. It was very good, I think. Yeah, I don't really have too much going on, but I'm still doing Coffee Talk every Moon Day morning. And that's
You've
about
been doing a lot of prep work for a new big esoterica event.
Yes, that is my new background project. So, yeah.
Okay. So that's kind of coming up and also kind of what you've been working on. So this esoterica event, it sounds like it's a big music festival. It's a little different than Flattoberfest, but kind of within the same time frame. But
right, it's definitely not like Flattoberfest at all. It doesn't really have the Flat Earth branding on it, but that's certainly part of it because that's a lot of what most of us are here for. But there's also more to it than that, symbolism, natural physics, like learning things that they didn't necessarily teach you in school, but are kind of simple things you can learn with children's toys that kind of give you a very simple and good idea of how this place works without having to process like a page of math,
So is there going to be like some speakers to that?
Yeah, there'll be, well, but it's not going to be speaker heavy. It's not going to be like Flattoberfest where there's a big screen and it's like, and everybody's like sitting there focused on the person and it's going to be more than that, more interactive and involve a lot more creative things, more the creativity side too, because that is actually a really important part of this place, of this realm, learning about the unseen forces versus the seen forces, because there's a lot more unseen forces than there are seen forces, right? And so learning about that in an outdoor, environment, in real life with other people and being able to be hands-on, there's just, that's what this is. It's much more about people learning in a more interactive way and through art and also music. If you make it fun, if you make it interactive, I feel like people will walk away with a lot more. You know what I mean? Does that make sense?
Yeah, absolutely. Yeah. It seems a lot more like music vibed, or music based. That's the whole.
Yeah, well, there's going to be live music, but there's going to be other things too. It's everything, but it's not. But the point is that it's not
just presentation focused.
It's not presentation exactly,
like slideshow
heavy.
Focused.
It's not that there won't be people talking and talking about these things. It just isn't going to be. It's just a different format. But
absolutely.
I think it's more fun. There'll be camping if you want to camp. You don't have to camp. There's hotels like literally 5 minutes away from the venue. It's very, very close. So I think it'll be really fantastic. It's 55 acres of nature land, wonderland, so it's cool. We didn't get to use it last time. And so I guess this is our chance to use it or lose it.
Totally stormed out this time, right?
Well, now going back to October is past hurricane season. So that's like, right, hurricane season ends September. Then you get October. It's actually much more mild weather. It's like 70s usually. I mean, think about the weather at the time we've had Flattoberfest. It's always been really good, mild weather around here. It might sprinkle or rain a little bit, but it's not a heavy rain season. those transitional seasons are the best time around here. So, yeah.
Cool. Amazing. So how's things going with you, Kemi?
Good, really good. Nice to be here, Kyle. I was going to say that the neat thing about the venue is, or the irony of the venue is we always love the dates at the end of October because the weather is perfect here year after year. It's the transition time. And we fell in love with the venue, but the venue was completely booked up in October. And I mean, they were booked up way, way in advance on it. And last year. So we took towards the end of September hoping, but again, we were a month out of where we normally are as far as in time and weather. And it was just the tail end of hurricane season in a place that you don't get hurricanes.
Exactly. Learn that lesson.
Learn that lesson. Now we're in the history books. We do get hurricanes now, or so. But anyway, no, the venue is beautiful. A lot of the things I know that somebody was saying on the occult and some of like the Sunday guys on Globebusters were worried about witchy, but not witchy. When you talk about occult knowledge, let's put in some of the things we'll be doing. You're right, it will be music heavy and arts heavy in that. But we'll have a Rubens tube or a fire tube showing what resonance is, which is showing you how natural physics works. We'll have cymatics. We will be doing different things. We'll have people that can again interpret the skies, go over constellations, and do things with you. It will be very interactive. We'll have, I'm hoping, drum circles. I know we're all talking about drum circles and different fires going around.
Yeah.
not witchy as much as like more of a festival, more interactive.
It's like family camping, but for people who are all about this type of information and who want to learn these, this stuff, this information, so that they can better understand what's going on in the world and how to make better choices for their life. That's really what it is. At the end of the day, what I've got from a lot of the stuff I've learned is I can make better choices. I can, live my life more informed in like the way I want to live it, and not just be pushed around by programming and, and all that stuff. So it's like just that type of environment. It's just a place to go learn, discuss with other people. You can bring people to this that aren't necessarily flat earthers, because it's not like, hey, flat earth event, if you come here, you're a flat earther. You know what I mean? Like,
it's a lot more encompassing.
Yeah, if you take that sort of, even though, really that's where it's coming from, but if you don't, put it in your face, you can allow people might feel more comfortable to come in and sort of talk about these things and get it, and and realize that there's a lot of us, who don't believe everything the media says, or don't buy into the two-party system, or don't agree with what the government's doing, et cetera, et cetera, et cetera. Don't want to have ourselves injected with medical experiments, that sort of thing.
Yeah, you just got to get out there and meet those like-minded people. It's not saying it's an echo chamber at all by any means, because any kind of group like that, there's always going to be someone who disagrees with another person. But it's nice to get together and do the social networking part and just be together. Know that you're not alone, as you said.
Yeah, exactly. I'm just telling Liz that the bugs are going to sleep in October, so she won't have to worry about getting bit all the time like she did when she was here in the summertime, poor thing. Anyway, yeah, cool. It's a beautiful time of year here, so I think it'll be lots of fun. It'll be what it should have been all along,
Yeah, absolutely. So I'll go ahead and show you a little bit about. One of the things I've been working on is I'm actually writing a textbook. This is actually chapter 1 of the textbook that I've been working on. And this kind of goes hand in hand with what we're talking about today. And so Earth science itself is a really broad topic. Okay, it covers astronomy, geology, oceanography, meteorology, and it's something that you see taught in high schools, but you don't really see it taught like as a whole like this in college. You don't see any specific classes called Earth Science in college. Instead, you just end up focusing on like one of the different subcategories of Earth Science. And we talk about departmentalization, right? And about how that happens so frequently. And unfortunately, that happens a lot in college. You get so focused on one of these categories that you kind of stop looking at the interaction about how one subject ends up affecting your view of another subject. And so that's kind of the focus of this textbook that I've been writing here. Is I'm trying to write an earth science textbook that's on the college level, kind of focusing on these interactions between how geology can affect your view of oceanography and vice versa, and yeah, all the interlapping sections. It's pretty fun. But in the past, for this whole Modern Earth Science Destroyed series, I started that with my wife years ago, and I've always been looking forward to this day where we can continue this on with you guys, get a bigger group going on here. And so we started this in my high school textbook because it was just kind of like a throwback to saying, okay, I want to go back and look at the books I studied as a kid and see how what it feels like now, kind of like watching a movie that you watched as a kid. You go back and watch it as an adult, and that's a very different movie now as an adult. And so it kind of works the same way with our textbooks. You can go back and read a textbook, and it's a completely different experience. And so that was kind of the initial idea that kind of got the ball rolling. But going forward, we've got additional textbooks. I don't want to just read out of one textbook. I've got a whole bunch of different textbooks here. So here is the updated version of this book. They're the same book. This one's just more current than the other one. And then this one is my college geography textbook. And we're going to probably be bouncing back between the different books kind of going forward. The total emphasis today is on longitude and latitude. I mentioned here that which is going to be a lot more of like the geology kind of based here. So any questions about that so far?
Nope.
No.
Please continue.
Okay. All right. Absolutely. Let's share screen and dive into that. Okay, working on that. Okay, this one is the college textbook, and this one's the high school textbook. I'm going to start with this one. And as we go through this, we want to look out for what I call academic pitfalls, places where the textbooks treat something as a claim, or they treat a big claim as a fact when they have provided no substantiation to that claim whatsoever. It's just, they're treating it as a fact and it has no foundation whatsoever. That's one of the things we look for. But we're not just trying to take everything we find in the textbook and just crumple it up and toss it out with the trash. We don't want to toss the baby out with the bathwater, as the claim goes. And so we're also kind of looking for things that we like in the textbook as well. Then, so take note of that. So we can just kind of take turns reading this. I've got links to this, and I'm going to try to provide links for all of the upcoming videos in the future. That way people can do kind of like the whole book club thing. All of this stuff is also going to be on the Miro board that I've got put together, where people can kind of do a combined research thing on that. Okay, so finding locations on Earth. Can you read all this all right?
We can.
Okay, I just want to make sure you can see it all right. Okay, I can go ahead and start.
I cannot see big enough to read. I don't know if we'll get. I've got reading.
It's okay. I can read it.
Okay.
Okay. So finding locations on Earth. We're diving into latitude and longitude. The points at which Earth's axis of rotation intersects Earth's surface. are used as reference points for defining direction. These reference points are the geographic north and south poles. Halfway between the poles, a circle called the equator divides Earth into northern and southern hemispheres. A reference grid of additional circles is used to locate places on Earth's surface. Okay. So we're talking about these parallels, the latitude and longitude, pretty easy.
So you could also think of it as, if you go back to that beginning, the points at which the sky's rotation define a reference point for direction. That's how we think of it anyway.
Yeah, absolutely. We focus on the sky. I was thinking about this and how the textbook makes this emphasis on the Earth's rotation. Okay, it was talking about that right here.
Mm-hmm.
The points at which the Earth's axis of rotation intersect. Okay, it puts a bunch of emphasis on that. And how many times do we hear claims about the Earth's axis of rotation changing? Right? Have you ever heard that? Where, oh yeah, they're doing something on some part of the world, and all of a sudden it's affecting Earth's rotation. Now, if that was true,
it was just affected 33 inches the other day by us building reservoirs.
Yeah, something like that. I've heard that.
Yeah.
So
there's something in the news all of the time, and you have to laugh so hard. But go ahead.
Yeah, if that's totally true, then the degrees of latitude and longitude would also have to be changing, right? If what this textbook is saying is accurate. But no one ever talks about moving latitude and longitude degrees. I thought that was pretty worth noting.
Well, they also always say it's too minute of a change for us, the layperson to measure, right? They're like, we measured it with the, our special high-tech, ultra sensitive LIGO, whatever.
Yeah. Okay. So latitude. One set of circles describes positions north and south of the equator. These circles are called parallels because they run east and west around the world, parallel to the equator. The angular distance north or south of the equator is called latitude. All right, pretty basic. Degrees of latitude. Latitude is measured in degrees, and the equator is designated as 0 degrees latitude because the distance from the equator to either of the poles is 1/4 of a circle, and a circle has 360 degrees. The latitude of both the North Pole and the South Pole is 1/4 of 360 degrees, or 90 degrees, as shown in figure 1. In actual distance, 1 degree of latitude equals 1 out of 360 of the Earth's circumference, or about 111 kilometers. Parallels north of the equator are labeled N. Those south of the equator are labeled S. Okay. Minutes and seconds, unless someone has something to say about that.
Nope.
Okay. We'll just kind of get through this, and then we'll jump over to the college textbook, read from that, and see how it's different. I really like comparing and contrasting how one book says things slightly different than another. Okay. Minutes and seconds. Each degree of latitude consists of 60 equal parts called minutes. 1 minute symbol of latitude equals 1.85 kilometers in turn. Each minute is divided into 60 equal parts called seconds. So the latitude of the center of Washington, D.C. could be expressed as 38 degrees, 53 minutes, and 23 seconds. Thought that was interesting how it's talking about that in minutes and seconds.
Like in terms of time almost, right?
Yeah.
Time is how we divide all of our measurements, by the way, the arc seconds and everything, time. And this is how time this is how space and time is related. I mean, we modeled space after that, and everything is where you are in time is where you are in space. So this is your original, and yes, all of our measurements derive from the arc seconds, and that gets into our time of seconds, and this is how it all began. But keep going.
Okay, so one thing that I'm noticing here is with our latitude and longitude is each of them are equally spaced, like perfectly equally spaced. I think it's about 69 miles between each degree of latitude, or between each degree of latitude, it's about 69 miles across per degree. And when we come over here, I wanted to share this. And I always thought this was really funny because this is the same book here, and they're talking about, Earth is a oblate spheroid. Okay, as Neil Tyson would say, it's pear-shaped. I got a clip we could talk about that. But yeah, can you see this?
Mm-hmm.
Okay, cool. Let's share this clip.
Can't hear it.
Can you hear it?
No.
Okay, I can try to fix that. Share screen. Got to remember to turn that to share audio, share tab instead. That's new. Okay, trying to get that to work here. Sorry about that. Learning curve. Share screen.
We could talk over and cover while you're doing it, Zach, but that would be too kind of us. And like we're making you learn on the spot. And
I know, sorry.
Can you hear it better now?
We're playing in the chat.
Yes, okay. Actually.
Yes, okay. It worked. Okay, perfect.
Find the farthest point from that center. And it turns out sea level at the equator is farther away from the center of the Earth than sea level near the poles. It has nothing to do with global warming and melting of the ice caps.
Why is that?
Because Earth, we know it spins once a day. Yes, thank you. 3 people know how long a day lasts here.
Good for row number 2. They're off to a great start.
So you spin, when you spin pizza dough, it kind of flattens out.
Yeah.
It gets wider in the middle. And so Earth, throughout its life, even when it formed, it was spinning. And it got a little wider at the equator than it does at the poles. So it's not actually a sphere. It's oblate. And officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
Yeah. Chubby's a good way. It's like pear-shaped.
Yeah.
So it turns out the pear-shapedness is bigger than the height of Mount Everest above sea level.
How much higher?
Okay. So
but we don't see it.
Yeah, we don't see it. And the big thing here is that the textbook itself was saying the same thing. Let's see. The textbook itself was making the same claim to the oblate spheroid.
Mm-hmm.
But at the same time, they're claiming that the degrees of latitude are all equally spaced apart, right? And so if it is oblate, then they should not be equally spaced apart. You follow that?
Say the last part again.
Okay. The textbook claims, each of the degrees of latitude form a perfect sphere. That's the whole thing.
Oh, I see.
It's all a perfect sphere, but the textbook also claims that the Earth is not a perfect sphere. They're claiming that the globe is oblate. It's pear-shaped, as Neil Tyson said.
Yeah,
right?
that's not even
if
a
that
pear
was
shape.
true, then the degrees of latitude are wrong, right?
That would make sense, except for they're going to, as soon as you start to argue that, they're going to all of a sudden say that your perfect sphere, that when taken from space, and you can draw like the perfect circle around it, but now needs to be the oblate spheroid for this. Also needs to be the geoid. That's my favorite. The potato thing
Mhm.
also. They'll just change their
They're like, well,
projections
we
on
know
you.
it's not a perfect sphere,
Perfect sphere.
so we use the geodetic, what is it? Yeah, the geoid, right? Like that's what
The
Shane
geoid,
talks
yeah.
about when he talks
Mhm.
about like how they do the map and stuff. There's three different things, and they're like, well, we're just gonna figure it, like average it out, because nobody uses a globe to navigate anyway, you know?
Yeah.
So
Yeah,
it's not like
absolutely.
everybody's going to be like, well, hey, there should have been a fight, they just don't, it doesn't make any sense, because every time you're navigating, you're so small compared to the Earth that you're using something local. And so when you're actually really navigating, your map is flat because it's like a small local area, and you don't really need to take into account the geoid and the height above sea level versus above the geoid and blah, 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 and all that stuff.
You do have
Yeah.
them there, Kyle, on a proof that they would have to be equal. They would have to be so now it's your job to like measure it out and find out
Yeah.
exactly where it's not, because again, they will hide it in going into different models and say, well, no, now you need to look at the geoid in order to do that from it. And again, your exact mileage doesn't work. They can get away with it pretty easy over land because we change altitudes, we have valleys, we have curves. I mean, we're not usually measuring as the bird flights are and that, but we're not. And that's all computerized now.
Yeah.
But I like the point. Did you find some places where it went out of balance on it, or we're just right now we're just learning our latitude and what it is? Because I feel like I'm back in, what grade am I in right now? Am I in fourth grade or?
The high school textbook is like ninth grade, and this one
I was
we're
gonna
flipping
guess
over to the college
7th.
textbook.
Oh, there is no way, you guys.
I was
School
gonna
was
say 7th.
harder when we were kids. I'm sorry, y'all are dumbed down if this is true.
No, that's true. They dumb people down. It's gotten
I mean,
easier and
they
easier.
dumbed us down sooner. I mean, they were having us do this stuff in I mean, this for sure was straight middle school stuff, but in old age middle school was, by the way, middle school was fourth, fifth, and sixth grade. Junior high was seventh, eighth, and ninth. But yeah, middle school, this is like straight middle school material.
Yeah. Some of the funny stuff on that note with dumbing down is I was noticing in this college textbook, they were talking about, like, I was taking notice of what they deemed vocabulary words, important words to remember. And one of the words that popped up was the horizon, talking about the horizon. Like, people don't know what the horizon is. What? Yeah, but college students, but yeah, that's kind of the world we live in today, right? Where adults don't know what the horizon means.
So, it is crazy. Okay. Yeah, keep going.
Okay.
So, you're flashing in and out, by the way, but just could be your energy.
Oh, that's probably it's the brightness and contrast determiner. It's my camera. It's when I move my hands around, it kind of confuses it a little bit. All right. So latitude and longitude. Here we are talking about that's kind of one of the things I liked about this book here, is the way that illustrated the great circles effect, for kind of putting a paper there in between. That was kind of a nice illustration. That the high school textbook, it did this similarly, but I just like this one better. Anyways, Latitude and longitude. Imagine you're traveling by car and you went to visit the Football Hall of Fame in Canton, Ohio. Using the Ohio road map, you can look up Canton in the map index and find that it is located at G6. The letter G and the number 6 meet in a box marked on the map. In G6, you can you locate Canton. What you have used is a coordinate system of intersecting lines, a system of grid cells on the map. Without a locational coordinate system, it would be difficult to describe a location. The problem that a sphere presents, however, is deciding where the starting points should be for a grid system. Without reference points, either natural or arbitrary, a sphere is a geometric form that looks the same from any direction and has no natural beginning or endpoints.
Yes.
So I think it's kind of talking about what you were talking about, Karen.
Mm-hmm.
And
right. So yeah, we always say that there's no up or down on the sphere, though. There isn't. That's why they use the sky, and that's the reference point. That's why in the beginning it's all based on Earth's axis, which is what they tell you is the rotation of the sky, is the Earth turning in a circle, but we know it's actually the sky's rotation.
Thank you. That's the whole spinning Earth thing is kind of one of those things that there's no observations of the Earth actually spinning. They'll make tons of different claims about that, and it's just been really interesting to dive down the rabbit hole on each one of them. I've heard about storm rotation. All storms end up rotating in the same direction. That's not true in a given hemisphere, but yeah, that's been debunked many times over. And so talked a lot about the Coriolis effect and that whole thing. Just yeah, it's been funny. I did a video a long time ago on tornadoes and about how in the northern hemisphere, a tornado is considered a storm, but not all tornadoes in the northern hemisphere end up rotating in the same direction. But they actually have they're called I forgot the name off the top of my head. It's a anti-tornado. Anticyclonic tornado, I think that's what it's called. Yeah, I thought that was pretty interesting. And then I always have to like look at their globes and see the different pictures of the globe with the different colors of water and all of that.
Mm-hmm.
You had something?
Mm-mm.
Okay. So measuring latitude, this is kind of a big deal. The North Pole and the South Pole provide two natural reference points because they mark the opposite positions of the Earth's rotational axis. Again, going on with that pitfall.
It's an antipodal cyclone, by the way.
Antipodal cyclone. Thank you.
I was going to say antipodal.
I was too, but I wanted to do that.
But I wasn't sure.
Because of magnetics, you're doing the same I was. And
yeah, I was like, antipodal?
Total.
Yeah.
I did the same thing, looked it up. I did go straight for antipodal, and it went into an antipodal cyclone refers to a theoretical scenario where two cyclones are located at opposite points on Earth. While not commonly observed or well-documented phenomena in meteorology, it's a concept explored in atmospheric dynamics to understand the vortex interactions and potential global weather patterns. Because they would need that for their little dipole hyperbole. It would be really, really, really distinct in their model if their model really did look anything like a dipole, but it doesn't. So they're going to be lost there. They're going to be lost.
Yeah.
We'll do magnetics later, but yeah, it does not look anything on paper like a dipole.
When it comes to latitude and longitude, it ends up being kind of a big deal, especially when it comes to like U.S. history and U.S. geography, because like so many different state border lines are actually based off of degrees of latitude. I think like part of the U.S. Canadian border, that's also determined by latitude.
Yeah, I mean, that makes sense. A big straight line that goes all the way across.
Yeah, good portion of that. And when you see those straight horizontal lines, Yeah, a lot of times it's completely latitude based. Measuring latitude. The North Pole and the South Pole provide two natural reference points because they mark the opposite positions of Earth's rotational axis, around which it turns in 24 hours. The equator halfway between the poles forms a great circle that divides the planet into northern and southern hemispheres. The equator is the reference line for measuring latitude in degrees north or degrees south. The equator is 0 degrees latitude. Yeah, it's kind of surprising that this is college textbook. You have to explain that those things. But
this is wild that this is a college textbook. I mean, a lot of the things having to do with grid coordinate system. I'm sorry, that was elementary. That was before you got to middle school.
Yeah. It's like, did you learn this stuff?
That this is college is embarrassing. For it really is. I mean, you look
it is embarrassing. The college.
This is no, it seriously is. And you watch other kids come in from different countries. You just came back from Sweden, and you watch people come in from Germany and different countries, and they pretty much say that until you get to postgraduate studies here, it's like remedial high school or even below for most of the kids coming. And if this is what they're putting out in college, this is embarrassing.
It's shocking.
Okay, shocking.
100%. Yeah. North or south of the equator, the angles and their arcs increase until we reach north or south pole at the maximum latitudes of 90 degrees north or 90 degrees south. To locate the latitude of Los Angeles, for example, imagine two lines that radiate out from the center of the Earth. One goes straight to Los Angeles and the other goes to the equator at a point directly to the south of the city. These two lines form an angle that is the latitudinal distance in degrees. That Los Angeles lies north of the equator. The angle made by these two lines is just over 34 degrees. So the latitude of Los Angeles is about 34 degrees north of the equator. Because Earth's circumference is approximately 40,000 kilometers, 25,000 miles, and there are 360 degrees in a circle, we can divide 40,000 kilometers by 360 degrees. To find that 1 degree of latitude equals, so this is, we're going into that, I remembered it right, 69 miles. 1 degree of latitude is about 69 miles. A single degree of latitude covers a relatively large distance. Sorry, jumping into a new paragraph here. But yeah, focusing on that 69 miles, okay? Remember, if it's an oblate spheroid, this is absolutely wrong. So it's one or the other, and this is where textbooks will contradict themselves.
But this is just talking about going north and south, right?
This is just talking north and south.
But it doesn't say the same for east and west between the longitude, right? Or what does measuring longitude say?
We're going to get there real soon.
Oh, okay.
I see it coming up, and it changes, but yeah.
Yeah. But yeah, in both instances, this is acknowledging we've got a margin of error. Okay. And so as we kind of go over this, let's kind of focus on that margin of error, and then we're going to widen it up to make it an even bigger margin of error. Okay. A single degree of latitude covers a relatively large distance. So degrees are further divided into minutes and seconds of arc. There are 60 minutes of arc in a degree. Actually, Los Angeles is located at 34 degrees, 3 minutes north latitude. We can get even more precise. 1 minute is equal to 60 seconds of arc. We could locate a different position at latitude of 23 degrees, 34 minutes, 12 seconds, which we could read as 23 degrees, 34 minutes, 12 seconds, south latitude. A minute of latitude equals 1.85 kilometers, and a second is about 31 meters. I feel like this is a big mouthful. That's one of the things I try to do. Like, if I were to be writing about this, I really want to put in the emphasis. Why does that matter? What's the big deal with minutes and seconds, right? So, but yeah, they're making a big deal about that. Can you think about
they
it?
do that to like do minute measurements in time rather than like something that's actually measured like physically.
Mhm.
You know, it just gives them a margin of error, like you were saying before.
Yeah. A lot of this kind of comes down to kind of viewing it like a clock and kind of figuring out the timing. But I think the timing ends up going a lot more when it comes to longitude than it does with latitude. For some reason, they want to try to measure it the same way, because that was one way. Now, that kind of gets me thinking a lot about how sailors have depended on clocks for navigation. I don't know if you guys have ever seen how knots are calculated.
They tie knots and run them out of a boat. It's fabulous.
Okay.
I mean, it's amazing.
Yeah, this is a chip log right here.
See the knot? I saw the knot go.
Yeah,
Almost
it's
there.
tiny, but you can see it.
You can still see that.
Mm-hmm.
Okay, so
That's cute, Karen, because that's why I turned my camera to the back camera, because I'm like 2 inches to the screen with my glasses on, and I didn't want to glare you all out.
So this is how I always found it really interesting how maps, when it comes to traveling on land versus water, they make a big emphasis on nautical miles, right? You can't travel the same way on water as you do on land. They always do this big, huge flip into different kinds of miles. And it's not just with boats that use the knot system, but they also do that in planes. In planes, they travel in knots. But this is the thing that they're going off of. And that's always really stood out really strong to me. It's like, what? Because it kind of reminds me about running on a treadmill. Where'd my treadmill runner go? Oh, sorry. Oh, fastest treadmill runner. Okay, so here we've got supposedly the fastest treadmill runner out there. Looks like he's going pretty fast, right?
Mm-hmm.
Treadmill's clocking in there at 26 miles an hour. Okay. So, but the thing to remember with this, as he's kicking his feet really fast, he's not actually going anywhere, right? 26 miles an hour.
Yeah.
But it's actually 0 miles an hour. So think about this as we think about measuring knots. Okay. You're just because your boat is pulling out a ton of knots, as long as that water is moving, you got to think about that water like a treadmill, right? That water can be moving out beneath your feet and you not actually be going anywhere, kind of like going upriver, right? And so if you're moving up a river, you're going against the current, you could be pulling out a ton of knots, but not actually be going anywhere. And this is something that sailors need to take into consideration. And so you can't just say, okay, I'm going to travel this many knots for this amount of time going north and I'll expect to be there, right? Because you have to take the water current into consideration. And I'm not aware of any sailors in the past that would really do that, especially out deep sea. How do you do that deep sea? Figure out the speed of the current.
Yeah, I guess that's why they started using the sky as a reference point.
Yeah. So much of sailing ends up being, okay, I'm gonna have an expected amount of time to get from point A to point B. And so much of this sailing was never going in a straight line, especially with sailboats, right? You go in a sailboat, it's not exactly a straight line path from point A to point B, but you end up following the river currents or the ocean currents, and those can be wiggly, especially going around. A lot of the sailboats ended up following along coastlines, and those coastlines aren't exactly straight.
Right.
So I always, when it comes to measuring things in speed or with a clock, that has always stood out really strong to me. Any other thoughts on that?
Not really. I always
Nope.
thought that, again, the knots, I always wondered about the currents and it pulling it. So it was nothing new to me. I just thought it was funny when I learned that nautical miles were by the knots, and
Literally by knots.
literally by knots. It kind of cracked me up, and it's like, oh my gosh, I went how many years without knowing that fact? So that was under you learn something new every day. And again, unless you have somebody holding the end of the rope and that you can pull it taut, you don't know how deep it's going, where it's getting carried underneath it, or, again, so many variables. It doesn't look like an over heavily weighted rope. So,
Yeah,
and the knots, again, it's cute.
We still use the nautical miles today, and I always thought that was just really funny because, it's about widening that margin of error. If you don't take wind currents into account, how many times have we heard as flat earthers people talk about traveling by plane from point A to point B, and because this plane is traveling this fast, this is our conclusion. I took a flight recently, yesterday. I was on a flight yesterday, and we arrived 20 minutes early. It's like, wow, good jet. We had the jet streams were in our favor this time, right?
Oh, and that happens all the time. I've been on planes where like you can arrive way more than 20 minutes early.
Oh,
you know, it's kind of wild. You're like, hey, we're 45 minutes early. What the heck's going on around here?
I think one of my all-time winners was over 2 hours early on it, and it was like, it wasn't international, but I mean, it happens, and you pick up that type of stuff, and it's like, nice.
Trying to measure distance by your arrival time is like trying to measure. I was thinking about like RPMs, okay, like in your car, right? You've got your you've got your tachometer and you've got your odometer, and one is really good at measuring how far you're traveling, but you never measure your distance with your tachometer, okay, your RPMs. You rev up your engine and you see the little meter kind of start to go up, and that's your RPM meter. And oh man, but measuring knots is like revving your engine. You might be going really fast, but not actually be going anywhere. And so, it's not the best way to measure distance at all. Do you follow?
Or you might be going really fast and on the current going even faster and fast. So, yep, I follow.
Yeah. Don't measure distance by expected arrival times, because a lot of things can end up jumping into that margin of error. Sometimes it can be accurate, but it's it's not the same way as it works on land. Okay, land is very dependable as long as you're going in a straight line, but it doesn't work the same way with water or air. Okay, sextants. A sextant can be used to determine latitude by celestial navigation. This measurement measures the angle between our horizon, notice here, okay, the visual boundary line between the sky and Earth, and a celestial body, such as noonday sun or the North Star Polaris. The latitude of a location, however, is only half of its global address. Los Angeles is located approximately 34 degrees north of the equator, but an infinite number of points exist on the same line of latitude.
Infinite. I don't know about that. I mean, that's just saying you can cut up your little point of measure as tiny as you want it to be.
Yeah, that is interesting wording. Infinite. So notice right here that they're talking about measuring latitude based off of the noonday sun, okay, or the North Star Polaris. And this one got me really thinking. I was thinking a while back to the Bible. Okay, you got like it's often referred to as like the Star of Bethlehem. The wise men ended up following a star to show them where Jesus was, and that was in the Bible. And I kind of started scratching my head on that one day, and I was like, if I were to look straight up and stand underneath a star, how many other people can do the same thing and say, oh, that star is directly above my head, right? 1 degree of latitude, as the book said, was 69 miles. And so I can be on one side of the room and another person can be way over on the other side of the room, really far away. I could get like everyone in my whole house or my whole yard. We can all point up to the same star and say, oh yeah, that star is directly above our heads. And so, but this here is saying kind of, you're arguing about like 69 miles of, that's how wide your margin of error is, okay, for how many people are going to stand under the same star, Polaris, and oh yeah, that star is directly above my head, and that's like a margin of error of 1 degree, okay. And so it's not really a precise GPS level kind of coordination system, okay. So hopefully you can kind of see how this is widening that margin of error even bigger, right?
It does. While you're doing this, though, too, on it, even with the margin of error, pay attention, because what you're doing and how you're finding geographic north on here by Polaris or by the noon sun, meaning like again meridian, when it crosses meridian by doing a sundial, and that is the same way you can determine what your magnetic declination is. You take your geographic north and you compare it to your magnetic north, and your difference is your declination. Are you deviating to the left or to the right? Is your like color shift that they show you? And that's simply all declination is a pressure mediation magnetically. But you are going to do what you're doing here. What they're doing, you're going to need to find what they call geographic north, and you compare it to magnetic north. And this they had to figure out a long time ago, because again, you don't always have sun, noon, you don't have exactly noon, or you have cloudy nights, so you're missing these things. So you kind of want to have an idea of where your compass is pointed, something that you can take with you and travel with it. And again, I think that like target map that says, east and west, and I believe that is a declination, that red and white target map, where it just writes in the countries and it tells you things, that crosses over right where a declination turns over. I think you're telling your sailors, this is when you're on this side, your compass is going to point left, and this side, your compass is going to point right in different degrees on where you are. And just give me a little. And then again, they kept it like recipes, the amount of degrees it shifted. But these were secrets going back through the BCs, and that they were at ports trading off declination. I mean, it was something that it was information you paid for. You highly traded, coveted, and you collected, the people collected declinations of different areas and would sell them, and that needed for sailors. So it's a whole fun area to go into. I took you off track, but what you're doing is the same way you measure for it. And we want people to, again, that make declination complicated, to like hear it in many different ways on how simple, and you can test it. By the way, that's something I would call esoterica, or hidden knowledge, how to understand your declination, how to understand your geographic and magnetic, and what these things mean.
I made a video teaching you how to measure your magnetic declination, if anybody cares enough to spend a day doing it.
I think there's a section that we'll probably talk about on compasses, and that'd be a great time to bring that up and kind of dive into a little bit more. Yeah. The focus here I was talking about is when it comes to determining your latitude based off of the position of the stars, it's not a precise thing where you're trying to find a spot and it's taking you to X marks the spot. Like, and so you got the wise men following there, and we're talking about like 69 miles of the general area. Okay. And unless that star is like really close to the ground. Okay. And that's the whole other question is, bringing into the whole thing on stars is definitely not what NASA claims they are, burning balls of gas billions of miles away. That star, it's got to be a lot closer to the ground if it's going to give like pinpoint accurate results.
That is a good point. That again, you have like that little circle that makes around it that all of the people are going to be just directly under according to measurement, your atmospheric and your different things doing with it. And then plus your target is moving. You got to keep in mind that your target is not like that. Your target is moving. It's not staying. It's not like it's staying there like a spotlight. So, oh well, we don't want to say anything like that with the Magi and that because that was magical and we're not understanding pieces of it. But it does add more magic to it that it was a moving target and they knew exactly where to stop and that. So,
let's see.
I take it they were looking at more than that. They were looking at a lot more than that, but.
Okay, so I wanted to let you see this here. Okay, this is the path of totality during a solar eclipse, right? And so this is going to be where you're standing directly under the sun. Okay, and I want you to see how wide that shadow is. Okay, because we're talking about like standing directly under the sun, right? Do you think that's a little bit bigger than 69 miles wide? I think it's
it looks definitely more than 69 miles. Yeah.
It can be, I think one person said it was like path of totality, about 300 miles. Okay. During a solar eclipse, unless that's talking about the penumbral shadow as well, but looking at the penumbral shadow with NASA's videos, they show the penumbral shadow being a lot bigger than that. And I had a good laugh about that. But
I think penumbral shadow is horse hockey, as Bob would say. I think it's horse hockey.
We didn't get it when we did it. We have balloon footage and that, so that also telephone.
You can't measure it. You can't like there was a penumbral eclipse of the moon in my area one day, and this was back when I was like recording eclipses and everything all the time, and I couldn't even tell. I was like, I'm supposed to be in full penumbral eclipse right now. Like, it's the same thing it did. You couldn't even see it could change, at all, like luminosity. There's nothing that I could see with my eye or with my camera. So I was like, I don't know how they're measuring this. I feel like it's just like, it's like their mathematical equation based on their BS, globe model. So like you have the umbra, which actually is the eclipse, and then their penumbra is their their BS that they, and then everybody looks for it and there's nothing there, and they're like, I must be dumb.
During a solar eclipse, there's that different kinds of shadows. Like there's the section where you're standing in utter darkness during a solar eclipse, right? The whole,
I do have your answer, by the way. I do have your answer. To view all the stages of a total solar eclipse, you must watch it from somewhere along that path of totality. Viewers outside this narrow, which is roughly 115-mile wide path, will only see a partial eclipse. Okay, so they're calling it roughly 115 miles.
115 miles about for the.
That looks about right, yeah.
I don't know where they're getting the 300 miles then from, because this whole image from NASA showing the penumbral shadow is huge, like covering
maybe the 300
pretty much.
Maybe the 300 miles is if you take it in the lengthwise direction, like how many people are seeing it at that, like given how long, how much length in the path. Could it be that?
I'm not sure. But my point here is, okay, you're trying to measure distance. Okay, that's what latitude and longitude is entirely based off of, or that's what it is. Okay, you're trying to measure distance based off of a position in the sky. And as I mentioned, latitude is a big deal when it comes to map making. And but here we've got a lot of wiggle room. Okay, I mentioned here that whole 69 miles over just 1 degree. And okay, with the sun, if you're to stand under the sun, we've got anywhere in that path of totality, that really wide path of totality of you said about 115 miles, right? Everyone standing in that shadow of the moon during a solar eclipse, they're all going to point up above their heads and they're going to say, oh yeah, the sun and moon, they are directly above my head, right? Okay, that's 115 miles of your margin of error. Okay, it's definitely not a precise thing when it comes to measuring distance. Okay, and map making. I thought, yeah. So people like to think about it like that way, but no, it's not precise. Huge margin of error. You follow?
Mm-hmm.
Okay. Measuring longitude. To accurately describe the location of Los Angeles, we must also determine where it is situated along the 34-degree north latitude. However, to describe an east or west position, we must have a starting line. Just as the equator provides a reference to latitude. To find location of east or west, we use longitudinal lines, or longitude lines, which run from pole to pole, each one forming half of a great circle. The global position of the 0 degrees east-west reference line for longitude is arbitrary, but was established by international agreement. Like, people really agree on all that stuff. But the longitude line passing through Greenwich, England, near London, was accepted as the prime meridian, or 0 degrees longitude, in 1884. Longitude is the angular distance east or west of the prime meridian. Okay, so that's kind of a big number to remember right there. 1884. That means all the years before that, they did not have longitude. Longitude is a relatively new invention. And yet, how much have you really seen the maps change since 1884?
Well, the longitude has changed.
Mm-hmm.
I think I do remember seeing some old maps where the longitude was in a different position than in Greenwich. But that's a pretty old one because, as we know, Britain was like basically trying to take over the world at some point. So
yeah, the whole British Empire.
So they're like, we're the middle, we're the center, everything starts here. But that is arbitrary.
Yeah. It's kind of a made-up position. I think that's kind of
because it's a circle, right? There really is no beginning and there is no end. So you have to arbitrarily make one up. But they based the center of that circle on the sky clock, the luminaries, because everything revolves around the center. But once, so they just have to pick an arbitrary starting and stopping point. That's what it is.
Yeah. One of the things that has kind of stood out to me has been the way the latitude and longitude lines are shaped. I'll try to show you a picture of that real quick. Okay, so with our degrees of latitude, they all kind of start from an epicenter. Okay, they start with an epicenter, and then you get these little larger and larger circles as you go further and further south until you get to the equator, and then they start to shrink again. But longitude is not that way at all. There's no circles that are growing and shrinking. And I thought, isn't that interesting how they do that?
The latitude lines are circumpolar.
Mm-hmm. Kind of, I think a lot of that has to do with based off of your position of Polaris, as we talked about earlier. And that's why they radiate outwards.
It's copying the movement of the stars in the sky, and the sun. I mean, the equator, they call the equator the Earth's center, but it's basically what it is the center of the sun's path, because the sun doesn't go beyond the tropics, right? So there's the Tropic of Cancer and the Tropic of Capricorn, and there's 47 degrees from tropic to tropic, and the 0 point is the middle, right? Which is 23 and a quarter, which is where they get their tilt from, right? But it's just the path that the sun stays in between, and it goes in between those two tropics, and it distributes its warmth, that way around the earth, and it just works because brilliant creator made this cool system that works on a circuit and just does what it does and keeps us all happy and alive. So,
Yeah. So when it comes to determining your longitude here, we don't have any kind of fixed star kind of that we're kind of watching.
No, that part's based on the sun.
Yeah, it's based off the sun. Yeah.
Because the stars don't travel tropic to tropic, right? Only the sun and the moon do that, and some of the planets, but
which makes a big deal when it comes to that margin of error. As I mentioned with the shadow of the sun, all those people are going to be pointing to the same position within 100 miles and saying, yep, the sun is directly above my head. Okay. Or out on the horizon. They're all going to be doing that. And so it kind of reminds me a little bit about, it's called sun glitter, that path of the sunlight that you see in water. Right. And so that it's interesting how all these different people on a beach can all be pointing at, or can all see that sun glitter, the path of the water going directly to them individually, right? And they're, oh yeah, that path is coming directly to me, and but they don't.
But it goes to everybody. Everybody sees it goes to themselves, right? That was part of my big realization about how the sun works. It's like, the reason the sun might not be a physical object, it's just that your body, and this is a sort of little off topic, but you are the antenna that is receiving that signal, and that signal is meant to go to you individually, and everybody's receiving it for themselves. So of course they all see the sun go to themselves.
Yeah.
It's so just sort of a weird thing to think about.
Do you think that's going to affect longitude at all? Like our whole understanding of longitude?
Well, yeah, because the sun is it's like it's there's a source of it, right, of the signal. So it's just your relationship to the source of that signal, but there being multiple poles and stuff, there's multiple sources. It gets complicated.
It's kind of hard to see a good. Oh, there we go. There's a nice example of our sun glitter, kind of that light in the water coming directly to you. But
right, it always goes to you and 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 to you. You know what I'm saying? Like it's very fascinating to think about that way.
Yeah. And how many people can it's the margin of error is a big deal when it comes to all of this. And so when we acknowledge it, because that's one thing so many globe earthers just refuse to acknowledge whatsoever, is that margin of error. And when we kind of want to destroy it, that whole concept, because anytime you challenge the globe, you can't challenge the globe without also challenging latitude and longitude. And so as we challenge latitude and longitude, it's blasting a hole and really exposing how wide their margin of error really is, because they'll try to minimize it with all kinds of things. But yeah, it's a big deal.
Yeah, but at the same time, it works for navigation.
Well, to a degree. And so
that's actually to a degree.
What you did there.
To a degree, yeah. Very penny. Very penny.
Totally unintentional, but it works.
You didn't mean to do that?
No, I didn't. It's just
that's hysterical. I thought you were that quick. I'm not sure.
No, I wish I was that quick. It just had kind of a little...
But where does that saying come from? Is that where it's from? because that's a common old saying.
That's
And now we have to find out the
exactly.
origin of that saying. Is that where it's from?
It
Works to a
probably
degree.
is, just like the nautical mile is from, damn it, that's from knots. How many knots they
It's
count?
to a degree. That means within 69 miles or 111 kilometers.
I'm looking it up while y'all are
And
talking.
also, whenever, when I started doing this, back in the day, and we're measuring sun angles, like anything within 2 degrees, if you're physically measuring the sun using whatever method, is an acceptable margin of error. 2 degrees, right? The width of the sun is like half a degree. So.
Okay. Like latitude, longitude is also measured in degrees, minutes, and seconds. Imagine a line drawn from the center of the Earth to the point where the north-south running line of longitude that passes through Los Angeles crosses the equator. A second imaginary line, meridian, crosses the equator. This location is 0 degrees east or west and 0 degrees north or south. Shows that these two lines drawn from Earth's center line and define an angle, the arc of which is the angular distance that Los Angeles lies west of the prime meridian. 118 degrees longitude provides the global address to Los Angeles by latitude and longitude. Wow, that is a mouthful. I don't like the way that was written. But yeah, I think they're talking about figure 2. Wait, is that the right one? Figure 2, 6. I think it's flipping back to here. Okay, yeah, they're talking about kind of this whole thing.
Yeah, it's distance. It's basically how long it, or how many degrees, an object in the sky travels before when it's like over Greenwich to where it's over over Los Angeles.
Yeah. So most of the flat Earth maps that I'm aware of show that the further south you go, the wider and wider our degrees of longitude become. And we talk a lot about plane flights, and we talk about boats going out there.
Is this so because we have a boat? No.
That's one thing. That's one place where they should kind of agree with us. With if it's an oblate spheroid, then they do get wider. Okay, the degrees of longitude, they do get wider the farther south you go for a little while, and then they start to come back together on their model, right? But they claim it's a lot smaller than we do. But yeah, a lot of those claims that they're making there about that widening degrees of longitude are all based off of our planes get there at this speed and our boats get there at this speed, and they're trying to do that whole thing on that I told you about when it comes to measuring with RPMs rather than your odometer, right? Kind of not taking any account for the speed of the water or the speed of the air that they're traveling in. Okay, so now we're going to talk a little bit about sextants. Okay. Which is kind of a big deal. I always have to point out that eye level horizon there in the background, which is how sextants work. A lot of sextants have been brought up many times in different flat Earth discussions. I think
I have a sextant on my counter behind that, by the way.
Sorry, what?
I do have a sextant right here.
That's not a sextant.
That's a sextant.
It's a sundial.
It's a sundial. Sundial
Okay.
compass and different, yeah.
Sundial compass. I don't think I've ever even heard of a
sundial compass is like basically how they used to tell time before clocks. Before that, or without clocks. It's based on the sun.
Yeah, I've seen a lot of sundials before, but I've never heard of a sundial compass Which
well, because it has a compass on there, so that you a sundial compass. I mean, to use a sundial properly, it has to be associated, to north or south, whatever. It has to be associated north-south. And so the sundial compass is a sundial and a compass, just basically in one is what it is, so that you can you level it and then you associate it to north, and then you tilt up the gnomon on the sundial based on your latitude, your degree of latitude, and it tells you the time. Very accurately, by the way. There's like on the face of it, it has like the hours of a clock engraved. So
it does.
tells you.
She's right. Yep.
It's basically a clock.
Trying to get you to get your screen a little bigger there. Oh, okay, I see the compass now on the center.
Yeah, the compass is on the bottom, and then the sundial part lifts up to match the latitude.
It does. You do the gnomon. It's got little levels. You have a level on it, so you have to set the, and it's filthy from being outside. You have to set the little feet on it, level it, and then there's your little clock face, and you set it. And notice your little bubble right here. That's your bubble level. Does not work unless it's level. Like most things. So there's your little bubble, your little beat to adjust it, your clock face, your gnomon.
Cool.
And she's right. I'm sorry I called it a sextant. I do have a sextant. It's in the other room, not right here. But this one was right there. There we go.
Very cool. Thanks for sharing. Let's try to switch her.
That, by the way, on the big screen, if you see it, up to the left, your first thing that looks like it's water running to your left behind the dam, that is a reflection of my camera. It was only for my camera that it was picking up, going right towards me in the camera. Not the stuff going straight, but if you see the first one up to the left, top of my screen now. And it's time, but yes, it was just a reflection that's walking right up to seeing the sun do it, and different than the water flow. You can see it's completely different. It's on the bottom water. Okay, go ahead with your sextant.
Okay. Trying to.
I was just noticing because I'm looking at the reflection right now coming right to me after we talked about that, and I'm watching it happen perfect right now.
Okay. Like latitude, longitude is also measured in degrees, minutes, and seconds. I think, did I read that one? No, I didn't. Okay. Imagine a line drawn from this. Oh, wait, I did read that. That was a big mouthful. Okay. Our longitude increases as we go further east or west from 0 degrees at the prime meridian. Traveling eastward from the prime meridian, we will eventually be halfway around the world from Greenwich, in the middle of the Pacific Ocean at 180 degrees longitude. It is measured in degrees up to a maximum of 180 degrees east or west of the prime meridian. Along the prime meridian, 0 degrees east and west, or the 180 degree meridian. East and west designation does not matter. And along the equator, 0 degrees north or south, the north to south designation does not matter and is not needed for indicating location. That's another big mouthful. I don't like the way that is written. Yeah, I think that's what they're trying to talk about. Is right here, they're talking about how it's 15 degrees on this side and this side. Yeah, I feel like bad writing loses attention. And as a teacher, maintaining that attention is like really important. The best educators know how to be entertaining and in order to captivate that attention. You know what I mean? Okay, so that's kind of one of the things when I'm writing my book, I'll try and do a better job of wording things and really kind of focusing on why that matters. Okay. Every point on Earth, Every point on Earth's surface can be located by its latitude north or south of the equator in degrees, and its longitude east or west of the prime meridian in degrees. Lines that run east and west around the globe to mark latitude, and lines that run north and south from pole to pole indicate longitude from the geographic grid. Okay. Feel like we already read about parallels and meridians. I'm gonna skip over that one. Forgive me.
Well, that's just another name for longitude and latitude, right? Parallels are the latitude, and longitude is the meridians.
Oh, that's yeah. That's true. So I don't think they even mentioned that, but that's a really good point. Yeah, you always talk about the parallels, but you never describe your degrees of longitude as parallels.
Because the meridians aren't parallel, they intersect at the poles.
Yeah. So yeah, great point. That's something that they definitely don't talk about, but I'm glad you brought it up.
I mean, that's what I thought it was going to say.
Well, let's do parallels and meridians. Now we want to know. Let's do this. I put my glasses back on. I still can't read.
Oh, it does. It says latitude is the parallel and the longitude is a meridian. That's what it says.
There you go. Okay.
Oh, okay. Yeah, east and west
Zinga.
lines completely circle globe. Okay. Yeah. Yeah, latitudes are parallels, meridians are longitude. Yep, right there. Talking about that. Okay. Longitude and time. Relationship between longitude, Earth's rotation, and time was used to establish time zones. Until about 125 years ago, each town or area that was known as local time. Sorry, let me read that again. The relationship between longitude, Earth's rotation, and time was used to establish time zones until about 125 years ago. Each town or area used what is known as local time. Solar noon was determined by the precise moment in a day when a vertical stake cast its shortest shadow. This meant that the sun had reached its highest angle in the sky for that day at that location. Noon and local clocks were set to that time because of Earth's rotation on its axis. Noon in a town toward the east occurred earlier, and towns to the west experienced noon later. I feel like that's a lot of words for a really simple concept.
Now, on your simple concept, I'm going to go out here too, because it is a mistake some flat earthers make, but when you delve into it, there are funny stuff going on with our time zones, and it is something that we need to take into consideration when doing mapping on flat earth.
Mhm.
But one of the things that is not, there are two areas that they'll sit there and say, well, we have this many time zones, and that doesn't make sense. A lot of the countries, especially some of the Muslim and more religious countries, will have multiple time zones where they have little time zones set. And you'll see where they're off 15 minutes. They have it over when it is high noon over their temple in town and that. So a lot of them will keep natural time, and natural time is very, very important to them. It's like observing sundown, sun up and sundown. Keeping natural time is important to a lot of people still. So you will have a lot of little isolated. So when you see like these small time zones next to each other, especially in the Middle East on some of the time zones, there's weird areas peeking in. They have it for religious reasons. The other thing is there is funniness going with the Antarctica, but you'll look at Antarctica and find out that a lot of the times they set their time zones in the Antarctica to just match up with the base that they're working with. So that's why you'll have time zones that are 14 hours away from, like, right next to each other. It will be because they're different bases that are just observing. They want to be on the same time as their scientists and who they're working, their families and that. And so it has nothing to do with natural time there. It has everything to do with work efficiency, and that's where they'll set a time zone. So you have two things. You have real things that knock you out of it. Now they've knocked us out and have broken us away from the concept of natural time as much as they can. They really try to mess with this. We spring forward, we fall back. We're out of time all of the time. People forget what it means, but noon meant high noon was when the sun was at its highest. And the witching hour, which happened once a month, is when you had your full moon and it was at the highest position in the sky, marking midnight. Your sun does it every day, but your moon, a full moon, only does it once a month. So that is your witching hour. Esoteric again. But natural time always worked like that. That was normal to set it based on noon was high noon and the witching hour and your day and night.
I'm glad that you brought all that up. I never really thought about all the different time zones when you're standing at like the North Pole. Okay, if you stand at the North Pole and you're up there, how many different time zones are you? You talked about the Antarctic bases and about how each one has its own base, but it's like you move over like a couple feet or a mile. Oh, now I'm in a different time zone. I'm like, what? Yeah, it's just kind of.
But yeah, I see that you do have
think
a map
all
there.
of the North Pole would have a single time zone, but yeah.
But they set whatever they want to. It's something that we arbitrarily name. We move the borders to go along with rivers. I mean, it originally meant that they tried to normalize time and make it a little bit so everybody didn't have their own time. So you pick certain areas. The midpoints have been said that a half hour in either direction for when your noon is, and that is your time zone. But you can see that if that was the case, you'd have beautiful little wedge time zones. And don't. I have that same watch here that's on my desk somewhere. I have that exact same colored like that in the whole bit in the little desk clock. But yeah, as you see the time frames, and then if you look in the Middle East and see where you have pieces of blue inside of the purple and different things like that happening, again where it jumps over and about, and they might not even show some of the small ones, but a lot of those are for religious purposes. I don't know if they're even showing a bunch of the little bitty small time zones that again just keep themselves actually in perfect time with other things around them going rogue.
Yeah. Time zones are a really funny topic, but I'm just thinking about how quickly time zones will change way up here, which I think is kind of ridiculous. I would think that it would just be determined that the entire North Pole would just have a single time zone, but nope. That's really funny. I'm so glad you brought that up because of how funny it is. There's so much about that. So time zones. I always like to point out how China, which is about like the size of the U.S., very comparable. How all of China has a single time zone, but over here in the U.S., I don't know how many time zones we've got here.
Right, they did that for business to keep it easy and everybody on the same. They take them all out of time. We're still a little bit out of time, but yeah, they did it for. Now, what turned out happening when they did do that, if you go over to China, you'll just see that school and businesses start earlier in one part of the country than the other. So you still have to adjust for it for the fact of when it gets light and dark and that. And so it didn't really work as homogenous as they wanted it to. But like when talking with everybody, you don't have to adjust for the time frame. And some people go to work at 5 in the, what would be again.
It just goes to show you people will just do what they need to do at the time they need to do it. The time is an arbitrary number. They're still going by, daylight, nighttime, whatever.
It's really wild when just flying back from Sweden, traveling through time was just really crazy. It's hard to describe all that. Just kind of.
I will point out that while you say it is arbitrary and everything, it really, again, it was always marked throughout time to mark these certain sacred, like when the sun was at meridian, when the witching hour was, and you're marking natural phenomena happening. So I don't know if it's there. I do know that when China and the different places,
well, these the weird time zones are arbitrary. Like they're not always in sync with the sky clock. It is
the ones over. Yeah, they're not. They're not in China. It's not at all. But the small time zones, a lot of the times, are specifically to be in sync with the sky clock on the religious ones. And China, which is non-religious, I think that they do everything they can to have people not looking up at the sky since it takes them out of time. I would say when you have one time zone over all of the country, one of the things it does do is it takes you entirely out of time and you lose what the meaning is of time. That noon has nothing to do when the sun is at its highest, or again, just even though you call it arbitrary, we've observed all through history. We've marked these as special times, and now we don't even know what they mean.
Yeah.
Noon to us now means 12 o'clock.
I also think I remember hearing that China based their time zone on the part of the country that has the majority of the population. Which is towards the East
So
Coast.
a lot of time zones is just a political determination.
Correct.
Yeah.
And
political, geographical.
It's really interesting watching this time zone right here. Kind of wrap around the purple area.
Mm-hmm.
And it's commercially based too. I'm sure it has to do a lot with money. Money.
Yeah. The textbook here was talking about the relationship between longitude, Earth's rotation, and time were all used to establish time zones. Yet it doesn't talk about politics at all there. Yeah, it doesn't talk about politics at all there. I'm like, what?
That's funny because, again, if it was just longitude and time, you'd see nice little wedges and they would work perfectly just the way our longitude. And in fact, you would expect them to run right with our longitude and latitude, and you can run your time zones right between them. I mean, you already have a grid there. Why not use it unless it really doesn't work out and you want to distract people from it?
Yeah. Oh, that's ridiculous. I'm just like, yeah, I've never had so much fun reading textbooks before. Yeah. When going through college, this whole thing is just kind of, yeah, it was incredibly boring taking this class in college, but kind of going back and reading it again with the new eyes, it's just hilarious. Just seeing all these things, like, what are they talking about? Why aren't they talking about the politics involved here?
I'm still finding it hilarious that this is a college class just because I'm that old and this does not look like college material to me, but keep going. Maybe things are special in Utah. No, I'm just kidding.
Yeah, we studied this one over at the time. It was Dixie State University. That's when I studied it. Now it's called Utah Tech. But if anyone else has other textbooks that they would like to share, we're open to reading them. Okay, this isn't just like a closed set. Okay, if other people have preferred textbooks, okay, don't ever feel like it's got to be this pack. No, it doesn't. This is just the one I've got nice PDFs to. That's it. Okay, so we got solar noon. Okay, we got local time, what that means. Okay, by the late 1800s, advances in travel and communication made the use of local time by each community impractical. In 1884, the International Meridian Conference in Washington, D.C. set standardized time zones and established the longitude passing through Greenwich as the prime meridian. I think this is kind of one of those big instances of the U.S. trying to govern the rest of the world. Okay, so Earth was divided into 24 time zones, one for each hour of the day. Because Earth turns 15 degrees of longitude in an hour, they keep re-emphasizing this whole turning thing. It's just like, why didn't you just focus on the movement of the sun? We all watch the sun move, but no, they're trying to put it all on Earth rotation. Okay, so Earth was divided into 24 time zones, 1 hour in each day, or one for each hour in the day. Because Earth turns 15 degrees of longitude in an hour, ideally each time zone spans 15 degrees of longitude. The prime meridian is the central meridian of its time zone, and the established time when solar noon occurs at the prime meridian was established as noon falls for all places between 7.5 degrees east and 7.5 degrees west of that meridian. Another big mouthful. I'm like, yeah. I don't like the writer here in that case. They make a mess of things. The same pattern was followed around the world. Every line of longitude evenly distributed by 15 degrees is the central meridian for a time zone extending 7.5 degrees of longitude on either side. However, as shown in figure 2-9, time zone boundaries do not follow meridians exactly. In the United States, time zone boundaries commonly follow state lines. It would be inconvenient and confusing to have a time zone boundary dividing a city or town into two time zones. So jogs in the lines were established to avoid most of these problems. Okay, now we're kind of talking about the politics. Okay, so there's some, but I still prefer to mention it over there instead. All right. The time of day at the prime meridian, known as Greenwich Mean Time, GMT, but also called Universal Time, UTC, or Zulu Time, is used as a worldwide reference. Times to the east or west can be easily determined by comparing them to GMT. A place 90 degrees east of the prime meridian would be 6 hours later, while the Pacific time zone of the United States and Canada, whose central meridian is 120 degrees west, the time would be 8 hours earlier than GMT. For navigation, longitude can be determined with a chronometer, an extremely accurate clock. Two chronometers are used, one set to Greenwich time and the other on local time. The number of hours between them, earlier or later, determines longitude. 1 hour equals 15 degrees of longitude. Until the advent of the electronic navigational by ground and satellite-based systems, the sextant and chronometer were navigators' basic tools in determining location. So here they're saying that you determine your longitude based off of your local time in the time zones here. I think that's kind of weird.
That is kind of weird and not helpful because, again, they're not following. It would be one thing if they actually followed the rules, but they're not following it. And they say they follow the state lines. But I've seen it switch over mid-state. I've seen it switch for all kinds of crazy reasons, political, geographic, state, or even, again, Arizona plays in different time zones than California part of the year, and that because they voted against not doing daylight savings time. So again, I guess that you adjust for the universal time, but again, it doesn't. The boundaries aren't right on meridian, so that doesn't work. Are we winding down on this tonight, or coming to a closing place on it?
Yeah,
that we
this
can
is
continue
this is a
on,
great
or-
closing place. I think, I think this is a great closing place right here. I think they're just kind of going on to international datelines, but yeah, kind of, that's great.
I like this, and I like tagging it in time. I think it's really important.
Yeah, I kind of take notice of all of this here with this whole time zone, and we can see that it's got different longitudes, but the time zone doesn't exactly follow longitude right there. And so you're trying to figure out your longitude by local time. It's going to be all messed up. And so we're talking about those extreme differences. Over here, it's a little bit more longitude oriented, but if it goes further south, I don't know what's going on over there. That's a really straight line right there. So I don't know.
Yeah, and
But
Australia's got the half-hour time zones where there'll be like so many plus a half hour off, which is kind of weird. I don't know about any other place that has a half-hour time zone, although some of the more localized ones in the Middle East where they have to pay attention to the sun time.
Yeah,
half
5.5, 6.5, 3.5, 4.5.
That's
That
wild.
is again that's where they're paying attention with their tempos and doing that. So you can call it wild, and they're kind of zooming in a little bit on it, or I don't know, maybe they felt I think a lot of the topos are old, but again,
Oh, look at that. 3.5 right over here, just off the coast of the US. So I guess we have a little bit of that too, just a tiny bit.
Mm-hmm.
Okay, but I think we'll wrap that up. And I can share your esoterica clip here. And
Sweet.
unless anyone else has something to add. So I'll go ahead and leave links for next week. Later on, I'll do a post and share the links, and so people can follow along and do the reading. And I always know that the best comments always tend to come after the fact. You don't always think the best thing to say on the spot. And so I'll leave a link to the Miro board where everyone can share things on things that they saw in the reading that stood out to them later. So Karen, what you got coming up?
I think just coffee talk on Monday so far. Unless, I don't know.
what are we doing? What
you
are we
have
doing
any-
tomorrow? Are we live tomorrow, or is that just in the background and meeting with people?
That is an offline meeting.
Offline. Oh, cool. That's my very, very, very favorite. I'm excited
Yes.
for that one. I'm actually super duper stoked for that one.
Yeah.
Very happy.
So, we're just doing stuff in the background. That's kind of most of the stuff I do is in the background. That's just how it works for me. But I will be definitely back Monday morning for coffee talk. So all my regulars who like to be there, I'll be there.
Okay.
I keep
it.
Yeah, keep going.
Do you have any set topics that you're going to talk about, or just going to find out on the spot?
I don't. I just sort of look at stuff leading up to coffee talk, and then I just put little links in my in a little thing I have for myself for subjects, and I just go in there and I'm like, oh yeah, we could talk about this.
Topics at the moment. Yeah.
Something could happen between now and Monday that is, way more interesting than anything that's going on so far. So you never know,
Yeah, I hear you 100%. I really do. Yeah. How about with you, Kemi?
Oh, I have something off air tomorrow that's exciting for me. I've been doing and talking with a lot of people off air. Every time I'm ready to immerse myself again, and I think I'm done with big paperwork projects, something comes up and dumps right in my lap. I think this will be the last one I'm trying to wade through. But yeah, all of these little something about old retirement and this crap shit that you have to deal with when you're old. So when doesn't go broke or do things like that? But yeah, I've been buried in paperwork. I hate it. I'm trying to unbury and get more out there. Excited for our festival. I really am. I'm excited to play the ad, but I'm just excited to get together and what we do when we get together, and music, fun, and again seeing everybody. So try to get the energy up for that.
Anybody who happened to be at the one time that we did Solar Return Festival, which was more music and art, it's like more like that, which was really awesome and underattended, but it was because I did it at a time of year where a lot of people who are gardening and homesteading and stuff, they can't really leave at that time, so it's like not the best time for people to be traveling. So that event didn't really take off like Flattoberfest. So it's like that rolled over into the old Flattoberfest time spot, but not Flat Earth branded, but still Flat Earth is in there, plus other stuff, and a little bit of magic sprinkled on there.
Sprinkle on a little bit of the magic, but like again, the magic to me is understanding how it works. And Sandy and Sina is looking at the magnetic patterns, looking at the polarity, looking at the different optics and that. So I think we're going to go with the filters of seeing the unseen.
Okay. Do we have any Sunday plans for Globebusters?
We do have Sunday plans on Globebusters. We're doing, I know that Shane is presenting.
Oh yeah, he's doing a part 2 on the geodetic, on the map,
yeah,
on the datum.
On the datum set, he's doing the WGS 84 and the different datum sets through that and going over that. So a lot of it has to do with latitude and longitude. So that's going on Sunday.
perfect timing. So, yeah.
Exactly. They mix right into each other. And this is almost when I went into it, which a lot of people reading the comments, a lot of people like they're going to say the definition of datum and that. A lot of the times they just jump in way deep in that on where they're working, which is great. But giving some people some backup on what the terms mean, and that is helpful and good. So I think that they complement each other really nice.
Yeah. Well, I hope that we're able to do a lot when it comes to exposing the large margin of error on the globe when it comes to latitude and longitude. Yeah. We'll talk more about this coming soon. So yeah, I'll keep everyone posted.
And
It's
Mods
been
in the
extremely fun talking to you about all of this. You're saying something, Kimmy?
I was just gonna say, Mods in the chat, if you could drop the website to this, in case anybody is interested, not to the YouTube, but to the actual website on esoterica.world. I say that because I'm on the Apple and I can't do that. I can't look at the chat there without switching it over and going. So
I got it.
You got it. Excellent.
Okay.
Ready?
Yep.
Got sound?
And close out with that. Yep.
Solve the mystery. Esoterica, Music and Art Festival. Decode the mysteries of the occult. October 17th, 18th and 19th, 2025. Happening in Spartanburg, South Carolina at the Music Camp. Fire. Water. Air. Earth. Ether.
Featuring Austin Whitsitt of Whitsitt Gets It. Live music by Chief Crow. Mario Garza of Symbolic Studies. Artist Watson Atkinson. Live music by Alex Lowry and Christopher Crumb of Don't Follow Crumb. Plus more to be announced.
Decode the mysteries of the occult. Gain wisdom, shed fear. Esoterica. Go to esoterica.world for tickets and for more information.
Cool. Was that Liz?
That was Liz.
That is
All
Liz.
right.
Liz and Karen. Lovely, lovely. Wonderful. I'm very good job recognizing the voice. A lot of people have. I'm loving it.
Cool. Well, thanks for all. Thank you for coming and being here, and I look forward to next time.
All right. See everybody next week. Some of you guys on Sunday and everything in between Monday morning. And Karen, I will see you tomorrow, I think at 3.
Yes.
Yes. That sounds good. All right. Good night, everybody.
Cool. Peace.
Peace.